thankful to the organizers for inviting me to deliver a talk on the recent advances in applied mathematics. And especially thank to Dr. Ram Kewal for giving me the opportunity and always discuss about the research and other things. And all of you, I hope you will enjoy the lecture. And is my slides is visible to everyone? Is my slides is visible to everyone?
Yes, it is visual.
So I have tried in the title of the talk is the role of applied mathematics in infectious diseases. When the invitation came to me for deliver a lecture on faculty development program, that time I have seen the title of that program, and it is written that mathematical tools and recent advances in applied mathematics. So I thought there will be some application of the applied mathematics, and in the situation we are living in a situation where most of the people are always worried about our daily life. Why daily life we are worried? Because of that COVID-19. Due to COVID-19, we are arranging everything through online virtual. So I thought it will be better to give some flavor in the infectious diseases and how to control and what is the basic reproduction number and other things. So I am asking again, is my voice is clear to everyone? Is any problem, please let me know regarding my voice as well as my presentation. Please cooperate with me. Hello? Hello?
Yes, sir.
Everything is okay? Voice as well as slides?
Yeah, everything is okay.
Okay. So before I am starting my talk, I just want to clear that I am not a medical practitioner or an epidemiologist, or I am just a mathematical modeler, and try to find the mathematical model. That model will give the better representation of the infectious diseases, like COVID-19 is the main situation, and other, I suppose, dengue, malaria, and measles, like that. So, in order to understand these diseases, the main objective of my webinar is to understand the mathematical model and how to diseases outbreak, and to gain some familiarity about the basic reproduction number, how the basic reproduction number flatten the curve or decrease the curve, and to design some better treatment policies such that the people can survive with the better life. So my first question is, the mathematical model can give the overview of the infectious diseases? This is the first question. Is it possible that a mathematical model can represent the disease dynamics? So that I will try to give the answer in my talk. So when you will see some real world problem, this is just a real world problem. In the real world, everything can happen. So there are lots of interaction, lots of possible factors, and lots of measurement. Everything is there. So which are the most relevant to your mathematical models, and how that interaction can be interpreted in terms of the mathematics that can be done through the mathematical modeling. So when there are lots of interaction in the real world, we can't think which are the most importance and most are the most importance as well as most effective in the real world. That factors we have taken. Suppose there are a lot of interaction in case of some such a flood. Everywhere some flood is going on. So you can see that what are the main factors. So there are the road conditions and the government policy, but we are ignoring some factors that the people daily in their daily life they are using their they are abuse their road. There's some they are taking some materials to their home, and the condition of the road became miserable. So in that case, you will think what are the conditions are the most important. The most important condition, the government policy as well as the road condition. So we are ignoring the condition that's a less important. So that's why we are considering some interaction between that real world problem, like some logic. We are proposing some logic. Everyone can propose their logic in different way, but we are logic that can be used by using some diagram. After using that diagram, we are trying to write that logic in terms of mathematics. So how can we write in terms of mathematics? So in order to understand the logic, the people are doing the mathematics by using the some differential equations. The differential equations may be the stochastic differential equation, ordinary differential equation, partial differential equation, and some are using some linear algebra matrices, some are using game theory, etc. So there are different possible ways that logic can be expressed. So once we get the mathematical model, then we can use some tools to solve that mathematical model, and then do some prediction about the models. That models are able to give that exact result, or what we have seen in the daily life, in the infectious diseases, or just like flood like that. So these are the main thing that there are lots of problem here. So we are trying to recapitulate this mathematical model in terms of some logic. After that, that logic can be represented as a mathematical tool. And once we get the mathematical tools, that mathematical tools can be solved in different ways, say difference equation like that, and etc. etc. So once we get the mathematical models, then we can do some prediction about our daily life and diseases. And once the prediction is wrong, then what can we do? We can try it, we can reformulate the mathematical model such that the mathematical model can give the proper scenario of the real world problem. So these are the main things that we can consider. So in that case, I am considering infectious diseases. So let us try to understand some patterns of the infectious diseases. So you can see the first is measles. The measles is a well-known infectious disease. So in the graph, you can see there is a very few infection of the measles. But after that, in the middle of that graph, you can see there are high number of infectious cases, and then the infectious cases decreases. It may happen due to some intervention strategies like some vaccination and some maintaining the social distancing and other things. So you can see there are few numbers of cases, and there are high number of cases, and the cases has been decreased due to some intervention strategies. And in the second graph, you can see there is a very well known, that is the flu that appeared in the Philadelphia, that curve, that black curve represents the status of the Philadelphia. In the Philadelphia, you will see that there initially there are very few numbers of cases, and the cases has been occurred very high numbers in the 19 October 2000. 19 October, there are high numbers of cases, and again the cases is being decreased. And in the cases of St. Louis, if we consider the Philadelphia and St. Louis, you will see that the St. Louis, there are few numbers of cases, not like the Philadelphia. So the cases is being increased, and again the case has been decreased. So in the case of West Nile virus, there are few numbers of cases, and after that there are high numbers of cases, and the cases has been decreases. So you can see that all the diseases there is a high number of cases. You see that there are high number of cases and then decreases. Here also flu, there are high number of cases, again decreases. Again, there are few numbers of cases, the case has been increased, and after that the case has been decreased. So when the disease will outbreak and when the outbreak ends, this is the main thing. So it is very difficult to say when the disease will be outbreak, disease will be end. So in case of COVID-19, we are unable to predict when the disease will outbreak. So in case of that, you will see that the patterns is very few numbers of cases and again high numbers of cases, and the case has been decreased in case of. So we are trying to formulate this type of mathematical model. That model can give you this type of patterns. A very common scenario, you will see that suppose there is a susceptible people. So the people is free from the any kind of disease, free from the infectious diseases, and infectious disease can be spread through the contact. So if that susceptible people can come contact with the infected people, then there is a transmission of the diseases. So transmit the germ from the infected people, so susceptible people. And when the germ has been transmitted from the infected individual to the susceptible individual, the susceptible individual become the infected, and both the people become infected. So what happened? When both the people infected, the infected people may be dead. So this is a very bad thing that dead. So we are considering the recovered. So in case of very simple model, we are considering the infected people become recovered or become immune due to some become infected people become immune, and these are the case the susceptible population become infected, and the infected population can transmit the disease to the susceptible population. So both are infected and the infected population become the recovered. So in this case we can say that we have considered the very simple mathematical model that has been proposed in the 1927 by Carmack-McKendrick model. In the Carmack-McKendrick model, the Carmack and McKendrick proposed the model by Ronald Roche, and they have considered only three compartments. These three compartment only: susceptible population, infected compartment, and recovered compartment. So you will say this is susceptible S, we denote it as a S, and this is the infected compartment. This is we consider the IE compartment, and this is actually recovered. The susceptible population become recovered, so we consider the compartment as a R. So in a very simple model, we consider that now the susceptible, the population either susceptible and they are infected to the virus, and when they recovered, we assume that they got the lifelong immunity. After getting the lifelong immunity, they got recovered. So this assumption is only for the very simple SIR model, and that has been proposed in the 1927. Is still the model is being used for till now 2021, and this model will be used, I think, throughout the life also. So in the model, first we consider we ignored we write that model in the mathematical form, say a rate of change of susceptible population, a rate of change of infected population, and rate of change of recovered population. So for the simple case, we considered here only the interaction. We are not considering here the natural death rate as well as the constant source rate, because the disease life is too short in compared to the individual life. Suppose if we consider the individual as a human, so average life you can say 60 to 70 years, but the disease life only few days actually, virus life. So we ignored here the demographic effect. What are the demographic effect? The birth rate, death rate, and the migration. These are the three demographic effects. So we are ignoring here. So this model, you can see that dsdt equal to minus beta si. So interaction between susceptible and infected, and this coming to here, and the infected, you can, this susceptible and recovered class, these two classes are non-diseased case, because these two classes are completely susceptible. You can consider the recovered population, they are free from the disease. Also the susceptible population, they are free from the disease. But the recovered population free from the disease after being immune, because they previously was infected. So the disease only come from the susceptible to infected class. So the disease has come susceptible to infected class, and infected population can recover. This is at the rate gamma. Gamma rate, the infected class become the immune. So in that equation, you will see S and R, both the class are free from the disease, but only disease will come from the infected class. So these are the individuals. So we have to consider the system is positively invariant or bounded system. Positively invariant means all the population are positive, and you can see that when the disease will spread, the disease will spread only in the case beta si minus gamma I greater than 0. So if this is greater than 0, so beta into initial population S naught minus gamma into I greater than 0. So at the beginning, I will be increasing if beta S naught minus gamma greater than 0. So beta S naught divided gamma greater than 1, this term is positive, then the disease will appear. Disease will spread. So
Wednesday,
you can see that
Thursday,
this number
Friday
is the ratio
Saturday,
between coming in the ith compartment
Sunday,
and coming out from the ith compartment. This is the ratio. So this ratio is the coming in the ith compartment and coming out from the ith compartment. This is always greater than 1. If this is greater than 1, then this is will spread. So this number, this peculiar number is called the basic reproduction number. This peculiar number is called the basic reproduction number. So what is the definition of basic reproduction number? So basic reproduction number is the threshold number. Threshold number, why we are calling it a threshold number? Because the disease will spread if greater than 1, and disease will outbreak if less than 1, means DIDT less than 0. So disease will be outbreak and disease will be die out, means I will be decreasing function DIDT or I will be decreasing function. And if this is equal to 1, then the disease will spread linearly or some logarithmically. So we can say that this number is the threshold number, and this is the basic reproduction number. What is the definition of actually I will be decreasing function DIDT or I will be decreasing function, and if this is equal to 1, then the disease will spread linearly or some logarithmically. So we can say that this number is the threshold number, and this is the basic reproduction number. I will be decreasing function DIDT or I will be decreasing function, and if this is equal to 1, then the disease will spread linearly or some logarithmically. So we can say that this number is the threshold number, and this is the basic reproduction number. I will be decreasing function DIDT or I will be decreasing function, and if this is equal to 1, then the disease will. So this is the basic reproduction number and definition. The basic reproduction number, one infected population is introduced in the completely susceptible susceptible population and how many people can be infected. This is the definition of basic reproduction number. So this is the very simple mathematical model, and we will now try to understand if this mathematical model can give the dynamics that we have seen in the previous figures. So yes, the question is here. So this is a susceptible population. You will get a susceptible population is decreasing. So there is a susceptible population that is decreasing. This is the blue color decreasing, and this is the recovered population. Recovered population always increasing. You here greater than 0. So infected population is increasing, and this is the red color infected population. So infected population means there are few numbers of cases, and there is a increasing of the number and again the decreasing. So these patterns you will get the similar kind of pattern for the infectious diseases that you have seen in the cases. Here the few numbers of cases, there is a high numbers of cases, again decreases. So our mathematical model, simple mathematical model, can give an overview about the disease outbreak or epidemic outbreak. So you will say that few numbers of cases that is increasing and there is decreasing. Now the question is, if there is some real data, so then the question is not to be easier to correlate with the data as well as with the mathematical modeling. Now I will give another disease. This is the measles. Measles is actually a childhood. Measles actually is a childhood disease, and we considered here on the 4 compartment here ACIR model. ACIR means, suppose you know that previously I studied here only SIR model, susceptible, infected and recovered. Here susceptible population and recovered population both are free from the disease, means susceptible population always be free from disease, and recovered population they got the immunity or by some different method, by some using some intervention strategies, and they got immunity and they recovered. Only disease case is I. So here you can see that there are 2 disease cases. One is susceptible and recovered, they are free from the disease, and 2 infected cases, that is E, exposed, and I. So why we introduce the exposed class? Because in case of measles, you will say there is an incubation period or latent period 5 to 14 days. So what is the incubation and latent period? So when a susceptible, when a child become infected by the virus, immediately they are not getting the symptom. Means immediately when the child get the infected by virus, immediately it will take 5 to 14 days to expel the disease. So there is a latent period. This latent period, this class is actually described as a exposed class. In exposed class, so exposed class is coming from the susceptible and infected. So virus is coming, beta Si is coming to the exposed class, and exposed class become infected, this Ke infected, and the infected class become recovered at the rate alpha. So there is a demographic rate we include here. This is the pi, this is the constant short rate pi, and this is the demographic, and natural death rate for the all the classes, this is the mu. Mu is the natural death rate for the susceptible class, exposed class, infected class, and recovered class. So how can I find the basic reproduction number? Here you can find the basic reproduction number only. There is only one class for the infected class. So this will be greater equal to or lesser equal to 0, like that. So here there is 2 classes. So how can we find the basic reproduction number from this model, SEIR model, childhood model? So there is a schematic diagram. From the schematic diagram, you can easily form that model, and if you have any question in formulating the model, you can ask me. I will give you the answer actually. And So in order to find the basic reproduction number, we consider only the class that class are related to the disease. Disease actually the related disease means we can say here these are infected class. E and I, these are infected class. So basic reproduction number definition actually mathematically the R0 is the basic reproduction number. So R0 is a threshold for the stability of a disease-free equilibrium point and related to the peak and final size of the epidemic. So R0 is the threshold quantity for the stability of infectious disease and for the stability of the disease-free equilibrium point. So disease-free equilibrium point means where there is no disease. So there is no E class and I class. So in order to find the basic reproduction number, you have to use the disease-free equilibrium points. The system has a unique disease-free equilibrium point, say S0, S0 equal to pi by mu, and you can see here on the S dot equal to 0, E dot 0, I dot 0, R dot 0. So you will easily find the equilibrium point. Only disease-free equilibrium point is this, and you can see here these two class E and I class are free from are the infected class. So only disease is coming to beta Si. This is the interaction term, and so we divide the E and I class by using two functions F1 and V1. F1, this is the considering the new infection, and the V class, that is the disease progression. That disease progression means Ke minus Ke, which is coming here plus Ke. So class K is the disease progression. Here also the disease progression minus alpha I plus alpha I. So disease actually decreasing, and this is the disease progression class. So we consider here two class beta Si, and this is another mu plus K into A minus Ke plus mu into mu plus alpha into I. So this is actually the F1 and this is V1. F1 I told this is the new infection and V1 is the class. This is for the disease progression. Sorry. Now after getting this this two function F1 and V1. So F1 you can see beta Si and minus this one. So this will be mu plus K into A and minus K plus this. So these two class F1 and V1. After getting the F1 and V1, we can find the Jacobian matrix at the disease-free equilibrium point. So Jacobian matrix is this at the disease-free equilibrium point. So this is written here the procedure, and V also the same. You have to find the Jacobian matrix at the disease-free equilibrium point. So once we get the F and V, we find that FV inverse by using actually this procedure actually the next generation matrix or next generation method. So FV inverse. So this is coming here F, this is F, and this is V inverse. This is V, so you have to find the V inverse. So multiply F and V inverse. So you will get the eigenvalues here K and 0. One eigenvalue, this is this one, and another eigenvalue is this. So this is the maximum, and R0 is the rho into FV inverse. So you have to find the maximum or largest number of eigenvalues. So this is the R0 calculation, and this procedure actually is called the next generation matrix. Some people can use different way. Also some people can consider F and V in different method also. So this is one method in order to find the basic reproduction number. This is in another case. So please see here, these measles actually coming infected by the susceptible population that can be infected, and that infected period, that infectious period will come after few days. That's why we use here the exposed class. But in case of vector host model. What are the vector host model? Some malaria, dengue, West Nile virus. So how the malaria will come? The malaria, when the susceptible human, suppose you are the susceptible population, so you will be infected by the virus. So how can we infect it? The virus will not infect you. If the mosquito bites you, then you will be infected. So mosquito here the vector. So this malaria, dengue, this kind of diseases not directly infected, not host infected. So there is a chance of the infection when the mosquito bites you. So this is the vector host model. The vector host model is telling us there is a susceptible host, means you are the host, and mosquito is the vector, susceptible vector, and susceptible host that can be infected by the susceptible vector. Infected vector, this is the IV dash. So in that case, you will see that. So in the model, you can see that there is a susceptible vector and sorry. So in the susceptible host S is and infected host I is, and susceptible vector SB and infected vector SB. So in case malaria, dengue, West Nile and some other virus, that can be disease can be spread through the vector. Without vector, this is not possible. So that's why we use a different kind of model and how to find the basic reproduction of that different kind of model. The simplest vector model is this SI model, SIS, or a simply SI model. And you will see here that beta, these are the constant source root of the susceptible host and susceptible vector. This is the pi is and pi v, and the natural death rate here the susceptible host is mu is, and natural death rate for the infected host is mu is, and susceptible vector and infected vector has the natural death rate, that is the mu v. And this is the disease, new disease infection. Disease infection actually beta is, S is, and this is the infected by the infected vector. So this actually comes the susceptible host, and infected and susceptible vector, that is the beta v SB SI is, that is actually come to the infected vector. So this is, so in order to find the basic reproduction number, you can see here the two infected class, IAS dash and IV dash. So IA is infected host and infected virus, infected vector. So in that class, you have to find the same basic same disease-free equilibrium. So disease-free equilibrium, you will see that there are two disease-free. This is SI, SI is I is, SB, IV. So SI model, two disease-free equilibrium point you will get here. So on disease-free equilibrium, free equilibrium, SI is 0, two disease class IAs and IV, IAs and IV, two disease free equilibrium, two infected equilibrium point, two infected class or two disease compartment, and two vector population, SA is 0 and SV0. So SA is 0, so I equal to 0, so you will get the infected class pi is divided mu is, and here pi v divided mu v, two equilibrium points. And F1 you will see, F1 will be here minus beta S is beta is S is B, and another beta v SB is I is. So this is the F1, 0 S is beta is S is 0, S is 0 is defined here, and V SV0, SV0 is defined here, beta V SV0, and V1. V1 will coming from mu is plus gamma and mu V. Mu is plus gamma and mu V. So again you find that by using next generation matrix, F will be F is derived on del E, del upon del I, del upon del E, del upon del I. So F and V you can find, and then you obtain that next and obtain the next generation matrix K equal to FV inverse, and you will get here the maximum or largest eigenvalue is this, and this is the basic reproduction here. So I have discussed here two kinds of disease. One is there is no vector, and another disease there is a kind of vector. Without vector, the disease cannot be spread. So this case actually the malaria, dengue, and West Nile virus, and another one is the simple ACIR model. That is the kind of measles. Some childhood diseases actually. So these are the procedure you can find the basic reproduction number. So now the question is why we are interested in the basic reproduction number, why we need the basic reproduction number, why we started. This is the main thing. So the disease, the pandemic, the infectious disease, the outbreak of the infection disease is not new in the life. Everyone infected by some virus. Every time you can infect by the virus, and you can protecting the virus, you have to do the necessary precautions or intervention strategy you have to mention. So in that basic reproduction number tells you few things. So what are how fast the epidemic growth? That R0 will tells you how fast the epidemic is grow, and if the R0 is high, the disease will quickly give the peak. That I will see again. So basic reproduction number, this will give an overview what is the basic reproduction number. Suppose this is the sick person, this red color, deep red color is the sick person. That sick person can infect 2%. So the basic reproduction number is 2 in case of hepatitis C. In case of Ebola also same like that. In case of HIV or AIDS, so one infected person can infect 4%. In case of SARS also, SARS a kind of disease that has been outbreak before the SARS-CoV or COVID-19, and mumps and measles has the very high reproduction number. When this is childhood disease, this can spread it very quickly. One infected person can infect 18% or 18 individual. So basic reproduction number is very high for the measles. Mumps also high reproduction number, but very high reproduction number for the measles. So R0 is the peculiar number. You will see that you can find the R0 at the disease-free equilibrium point. So at R0 equal to 1, so this point is R0 equal to 1, and this point R0, this side, the left side R0 less than 1, and right side R0 greater than 1. R0 less than 1, that means there is no disease outbreak. Means one infected person can infect more less than one person. So there is a very decreasing cases, so disease can die out. And R0 can greater than 1, means one infected person can infect more than one person. That's why you can see that R0 disease will be outbreak, and R0 equal to 1, the disease can spread, that can be linearly or some logarithmically. So you can say that R0 is a threshold quantity that can give an overview when the disease will be die out and when the disease will be outbreak. So in the graph, when the R0 is very high, the peak is very high. So R0 equal to 10, the peak is very high. R0 equal to 5, the peak is high, but not like that R0 equal to 10. And when the R0 is very less, say 0 equal to 2, the peak is decreasing. So R0 tells you the final size of the epidemic and the growth of the epidemic and the peak of and size of the epidemic, like that. So R0 is a very interesting, very necessary. The population behavior have an impact on R0, being R0 being decrease or increase. Suppose if you use some intervention strategy, means if you use some masks and if you use the social distancing, that means that disease can not be spread so quickly. That's why R0 can be decreases. So the population behavior can have impact on the basic reproduction number. Another is the very interesting thing, that is the case fatality ratio. Case fatality ratio, what is the case fatality ratio? Case fatality ratio is defined here, the number of died person, how many person has been died due to say COVID-19, and divided the number of cases depends on number of undiagnosed or tested cases, means how many person are diagnosed with the disease or diagnosed with the COVID-19 after medical treatment. So which country has the most tested, their case fatality ratio will be very less, means when the disease diagnosed with the disease will be diagnosed by the medical team, then this denominator will be a very large number. So the number of person divided the very large number, it will be very low. So the case fatality ratio will be very low in case of diagnosis. So in case of COVID-19, I can say that the South Korea testing a lot to identify the COVID-19 cases, whereas India and USA tested very low. Therefore, the case fatality ratio for the COVID-19 in case of India and USA is very high, but in case of South Korea, the case fatality ratio is very low. Sorry. So in case of table, you can see that the R0 is very high for the measles and case fatality ratio also high. But in case of MMMUT, the basic reproduction number is very low, but the case fatality ratio is very high. So in order to understand the disease dynamics, you must have to know about the disease basic reproduction number R0 as well as case fatality ratio. So there are different kind of basic reproduction number. So first, the basic reproduction number that I have defined on infected people, how much infect the subsequent population. This is the basic reproduction number. And another basic reproduction number is called an effective reproduction number. What is effective reproduction number? Effective reproduction number is the number that you can identify at any time. At time t, say you can identify the effective reproduction number anytime. Suppose today is the effective reproduction number says 2. So today at 2 p.m. say effective today at 3 p.m. when I started my talk, at that time basic reproduction number is 2. So if you know effective reproduction number ratio, then you can say after my talk what is the effective reproduction number of COVID-19. So you can identify at time by time, at any time. Control reproduction number means if there are some intervention strategies has been undertaken. So you know the very common control measure that is called the control reproduction number, say lockdown. When you use the lockdown, that time the control reproduction number is being used. Means when you use some intervention strategies, that time you can use the control reproduction number. Type reproduction number means suppose you have a different age group. Suppose you want to give the vaccination for the COVID-19 and you divide the groups in three age groups, say 0 to 18 one age group and 0 to 18, 19 to say 45 age group 2 and 46 to others, that is age group 3. So there are type reproduction numbers. So you can give the vaccination at the group 1, group 2, group 3. So this is the type reproduction number. And invasion reproduction number is the multiple strain. Multiple strain means you can say the measles. Some vector host model. You can say malaria, you can use the invasion reproduction number, means you will find the different equilibrium points for the disease free equilibrium point, and you will find the invasion reproduction number. So this kind of reproduction number is exist. Now, all the things that I can be easily used, that how can we find the basic reproduction number, how can we correlate with the diseases, and how the simple mathematical model can give you the overview about the disease outbreak, but it is really difficult or nearly impossible to correlate the mathematical model with the real data, because that figure that I have shown in the SIR model, that figure you will see that there is outbreak and disease die out. But if we matched with the original or in any kind of diseases, then it is very difficult to match with the data and the graph. That's why we use some complicated mathematical model. That model can give you some overview about the disease outbreak and how can disease can be measured, etc. So in order to understand the disease outbreak, I can say one thing, the herd immunity is very important to know about the disease outbreak, how the disease can be spread. So you will see that blue color, here all the peoples are blue color, and that blue color not immunized but healthy, means these are the susceptible population, blue color. This red color, you will see that the red color, the not immunized but they can infect the disease, these are the infected class. So when two infected population remaining in the total susceptible population, that become all the infected, all the susceptible population become infected. So here few people are susceptible but most of the people are infected. So this is the effect because of two infected population. But if we include some immunized by using some vaccination, say, so that immunized people, if you include, then the susceptible immunized population, they are not being infected, but the susceptible population that being infected. So if we immunize or vaccinated most of the people, then what happens? That infected population that can infect the susceptible population very less. So that's why the disease can be eliminated, or the curve can be decreased, because most of the people are immunized, they got vaccinated, so they are not able to outbreak the diseases, that immunized person. But that's why the infected person can infected very few people, so disease can be die out. This is the herd immunity. So herd immunity, what is the definition from that figure? We can conclude that herd immunity refers to the indirect protection from the infectious diseases that occurs when a large number of people get immune through vaccination or previous infection. So if you previously infected, then there is a less chance of being infected. That's why a large portion of individual possesses immunity. Such people being that immunized person, they are unable to or they are unlikely to spread the diseases. So what happened? The most of the susceptible population, if they are get vaccinated, so they are unlikely to infect the population. That's why the disease can be die out, or disease can be disease spread can be stopped. So this is the herd immunity. So in case of COVID-19, there is a high chance if all the people get the vaccinated, so disease can be stopped. So in that, I just wanted to give an overview about the COVID-19 and how the different people are use mathematical model to eliminate the COVID-19 or to end the COVID-19. So that's why I just give on mathematical model of my own research work that can be explored here. So before giving the mathematical model, I just give a flavor about the COVID-19, a global pandemic. Throughout the world, as of report 16 August, throughout the world, these numbers of confirmed cases and whole lakh around the death occurred due to COVID-19. And this is the world overview. In you will see that the first outbreak happened in the Wuhan, China, and you will see that the COVID-19 daily cases, new cases, it's like that. It's sometimes is expected is high peak and low peak. It has taken but 7 days moving average for the daily new cases and daily deaths. So we have used the 7 days moving average, and you will see that the daily death, the death rate is very low in case of COVID-19, but the new cases is very high, but the death rate is very low. So in case of Indian scenario, you will say that there are very few numbers of cases, and first wave there are around 1 lakh, around 1 lakh people has been infected daily. But there is around February 9, 2020, or very few numbers of cases. But in the May, there is a high number of people, whole lakh, around 4 lakh people is being infected daily. So you can see that the peak of the first wave, the daily first wave of COVID-19 cases, and the second wave. Second wave, there are high numbers of cases, and the first wave there are few numbers, only 1 lakh. But in the second wave, you may see that there are 4 lakh cases has been around. So still the COVID-19 is going on. So. And the daily case also, that similar situation will happen when there will be good number of cases is being arised. That time the death will be increased, and they are also see that here the COVID-19 cases has been increased, and here the death is COVID daily new cases has been increased, and here also you will see that the death case also is being infected. And this is the graph. You can see that the new cases and the recovery. In the case of first wave, you will see that you observe that 95% recovered cases are there and 5% death also there. But in the second wave, 99% recovery data, only 1% is death. Very few number of cases has been death in the second wave. But I can summarize some of the cases when the COVID-19 has been outbreak. Not only in India, throughout the world, most of the countries have declared the lockdown situation. In India also, first lockdown announced March 25, and that first lockdown for 21 days, second lockdown for the 19 days, and so on. So all the countries has declared the lockdown to mitigate the COVID-19 diseases. So it is a very good process, very good to decrease the COVID-19. The primary step taken by most of the government of different countries of COVID-19 is the implementation of lockdown. This is an excellent process to maintain the social distancing or to mitigate the COVID-19. But there is a very big problem in economy. The complete lockdown may cause the significant crisis in the financial, not only financial, in the daily life also. In particular, in India, this is a high dense country. So in order to maintain the social distancing and reduce the COVID-19 cases, you will see that if the lockdown is continued throughout the year or throughout the time for indefinite time, then it is very difficult to continue the life for the daily for the people who are daily wager and daily worker. So there should be some policies that the by maintaining the social distancing to open the all the necessary shops and the places actually. So the rationale behind the lockdown and quarantine is that to regulate the high numbers of COVID-19 cases, because if there will be high numbers of infection due to COVID-19, then it is very difficult to get the bed in hospitals. That's why COVID lockdown is one of the main reason for taking the for maintaining the social distancing and maintaining the quarantine, etc., etc. That's why the lockdown is essential, but indefinite time is not accepted. So you can see that what happened in the case of lockdown. What happened in the case of lockdown? In case of lockdown, you will see when there is no intervention strategy is being made. So the peak is too high and peak is starting for here. But when there is a moderate lockdown, the peak is occurring in delays. There is peak started from here and there is peak started from here, but peak is not too high like the without intervention strategies. But when there is a hard lockdown, that peak is also there is causing delay in peak, but peak is like the similar type. But in case of hard lockdown, by introducing or incorporating the social distancing, isolation, etc., that time but the peak is occurring in delay and the peak is not too high compared to other peaks. So you can see it. So the effect of lockdown, what happened? The effect of lockdown not only reduces the size of the peak, but also not only reduces the size of the epidemic, but also causes delay in occurrence of the peak. So it causes delay peak. Peak is occurring, but in delay time. It will take some time in, but also epidemic size also decreases. So lockdown, the effect of lockdown not only reduces the size of the epidemic, but also causes delay in occurring of the peak. So lockdown is essential, but not for the indefinite time. So by keeping this in mind, all the situation, we have considered a mathematical model. This is, you can see that the susceptible population here, the susceptible population is here, and this is the recovered population, and these are the infected population. The dead population, this is something isolation who are isolated to hospital. This is the dead isolation, that class can be isolated, that can be dead. So in the infected class, we consider a class, suppose exposed class or latent class, because we all know the there is a latent period for the COVID-19. So latent period, after latent period, they may be asymptomatic or pre-symptomatic. So if they are asymptomatic, they can go to the recovered after some intervention strategies, and pre-symptomatic, they can be detected by the medical practitioner, and some can be undetected. So there will be some mild cases that cannot be detected also. So that undetected cases, they also can go to the recovered class. Pre-symptomatic itself can go to the recovered class. And another class, symptomatic detected, that can be if they are symptomatic and they can be detected by the medical treatment or medical test, so they can go to the isolation or hospitalization. If they go to the isolation or hospitalization, they can be recovered after proper treatment. But some cases, some of the isolated cases or some of the patients can be died. So they can be die. So these are the infected class. The modeler that can be used in different way. They can use different model, but this is we have taken consider some of the 9 classes here. The basic idea, the susceptible population and recovered population is there, and all other class they are the infected class. So the basic ideas is exactly the same. The basic idea, the formulation of the SAR model, and we divide the I class in different classes according to the assumption actually. So different people can give the different assumption to make the model. So based on the schematic diagram, we have formulated different people can say the different assumption to make the model. Class, exposed class, asymptomatic class, pre-symptomatic class, symptomatic undetected, symptomatic detected, isolation or hospitalization. This is the recovered class, and the population who are go to the isolated class. That isolated class goes to the dead class or extinct class, and the total population is N. And based on the assumption that the lifetime for the COVID-19 cases only 14 days around, that's why we are in compared to the human population, so very less the lifetime for the susceptible population and for the COVID-19 cases is very short. That's why we ignoring the demographic effect. This is logical, more logical to not considering the demographic effect. But it is very difficult to handle without the demographic effect. Anyway, we have not considered here to make the model more logical. So here you can see the susceptible population can go to exposed class, and then we can move to asymptomatic, pre-symptomatic class, and some are symptomatic, undetected, detected, and isolated class, JI, that can be died here or dead class. So we can consider only the dead from the isolated class. This is our assumption in our model. So in the model, we also find the basic reproduction number. So basic reproduction number exactly the same procedure. Then we consider the diseased class. Here the non-diseased class are A and S. These are the non-diseased class, and E, A, P, U, D, I. These are the diseased class. So we are consider F. F is the will be here. This is the new infection, and all the others that will go to the V class. Then we find the FV inverse, and then find the basic reproduction number for our model. And we also perform the some local stability analysis. That for the disease-free equilibrium will be stable at 0 less than 1, and unstable otherwise, and some other global stability that we find here, but we are not considering here. So in order to get the data, whatever data that we estimated the data from the Indian case only, Indian data only. So in the graph, you will see that the power law graph, you will see that the plotted in the y-axis t plus 1 at time data, and t at the t day the data is plotted. So this is t and this is t plus 1. So this data you will see that the well matched means you can see the data at t and t plus 1, they are relatively dependent, means they are dependent data. So we match the data for the daily new cases and daily dead cases. From that graph we are not estimated. This is the observation, preliminary observation of the data. The data are correct or not. So if this data is showing that the t and t plus 1 data, so this is just showing the very good message actually. So we can say the data is okay. So now in our model system has 13 parameters, say beta p, beta a, beta u. These are the contact rate actually. So I have to explain, I did not explain the terms actually. So this is the beta p, beta a, and beta u. These are the contact rates, susceptible and pre-symptomatic, susceptible and asymptomatic, susceptible and symptomatic, undetected. These are the contact class, beta p, beta a, and beta u. These are the contact class. So our model system has 13 parameters. So from the Indian data, it's very difficult to estimate all the 13 parameters. So which parameter should we have to estimate? And which parameter we neglect or we will not estimate the parameters. So in order to understand which parameters are most sensitive with respect to the symptomatic classes, that's why we perform the sensitivity analysis. In the sensitivity analysis, you will see that this beta p, beta a and beta u, these are the three most sensitive parameters. Also rho, gamma a, gamma p, these are the most sensitive parameters. So we estimated only 6 parameters from here: beta p, beta a, beta u, gamma p, gamma a and rho. 6 parameters we have estimated, and rest of the parameters we have taken from some existing literatures, as well as we assumed from the parameters, because we have seen that the rho is lying between 0 and 1. So we can take the value of rho between 0 and 1, and we have taken the value, we have assumed the value of rho that will give the better fit of our model. That's why we have estimated 6 parameters, and some parameters from existing literatures and some parameters from the assumed parameters. So some people may ask the question, all the population are positive, but why some population cannot showing the negative? Here not showing the population are negative, that cannot be. So we are doing the PRCs, partial rank correlation coefficient, so that can be negative with respect to the infected class or with respect to the other classes also that we have taken. But we have taken the classes as an infected class because we are mainly interested in identifying or decreasing the infected class. That's why we have taken the infected class as a mark. So with respect to that infected class, we have estimated the most sensitive parameters, and this parameter will be estimated with respect to the daily COVID-19 cases, cumulative COVID-19 cases, and total number of deaths. So you will see that the mass are looking good. So from that massing, we have estimated the parameter by using the least square method, and 6 parameter we have estimated, and you will see that beta p, beta a, beta u, these are estimated, and rho, gamma a and gamma p, this has been estimated, and others parameter has some reference, and other parameter has some assumed parameter. So after getting the parameters, this is the most toughest or most difficult task to find all the parameters. So once we get the parameters, now we can do some simulation of our model, that our model can give the our model can generate the figure that has been observed in COVID-19 cases. So that after achieving the parameters, now we will say that our model is able to give the figures or not, or give the overall dynamics or not. So this is also another difficult job, that our model is produce the most of the dynamics of the COVID-19 cases or not. So first we have estimated we have seen the sensitivity of the parameters with respect to R0. So with respect to R0, the most sensitive parameters is gamma A, rho, and beta A. These are the most sensitive parameters with respect for the R0. So R0 will be varied, or R0 can be varied, but most influentially, or for little changes of R0, or little changes of gamma A, rho, and beta A, the R0 will be changes heavily. So why we will need the sensitivity of R0? Because we need to control the disease. In order to control the disease, you must have to control the basic reproduction number. So in order to control the basic reproduction number, we have perform the sensitivity analysis, and in the sensitivity analysis we will do the model simulation with respect to this parameter. Then our model will give the very good dynamics, because to control the diseases. So in the beta A and beta P, suppose this is R0 equal to 1. This is blue, and the blue line where we marked here the black line, so R0 equal to 1. So beta P and beta A, these are the contact rates. So this left side, this side R0 less than 1, this right side R0 greater than 1. So if we see closely, very clearly, for the small value of beta A and beta P, the digits can be die out, because this is the bar R0 less than 1. This side R0 less than 1, this side R0 greater than 1. So if we are maintaining social distance, means beta B and beta A both are very low, that means disease can be die out. Means we are not together for the social, we are maintaining the social distance, that means we are not close together, then the disease can be die out. So you may see that if we not gather together for the cultural function or some gathering, or if we not arrange some functions, as well as if we close the school and colleges and everything, that time there is a very less chance of being interact. That's why for the less value of R0, the beta A and beta P should be measured. So beta A and beta P is less, means this contact rate is less than R0 less than 1. So you can see that for less R0, the beta A and beta P should be controlled. And beta A, beta P should be controlled means we must have to maintain the social distancing. So from our model, we can see that an interesting thing, if we less the contact rate, then the R0 can be controlled. R0 can be controlled means disease can be controlled. And here also, if we mention here the for the little value of gamma P and gamma A, the R0 can be mentioned here. And another thing is that we have plotted only 6 graph for R0. It is less than, the red curve is R0 greater than 1.2889, and the blue curve R0 less than 1, 0.7030. So if we mention the beta A, P actually, if we here beta P equal to 1.10, here beta P equal to 0.55. So you can see that if we for the lowest value of beta P, the R0 can be controlled. R0 can be controlled means for lower value of R0, beta P equal to 0.55, R0 equal to 0.7. So this curve is showing that for less beta P, beta P equal to 0.5. If we increase beta P, then the R0 is increased. So here also showing that if we increase, here we have shown that beta P, beta A. In the time series, we have shown that only beta P can be controlled, then the disease can be controlled. If we have maintain beta P equal to 0.55, R0 become less than 1. But in case of susceptible, that population can be increased. Because of this is the susceptible population, that susceptible population always be increased. So we have performed the short-term prediction. Actually, this is the previous one. So our model shows that the daily COVID-19 cases and cumulative COVID-19 cases as well as total death both are increased. So our model also matched with the similar kind of data, and we also plotted the R0. This is the view. This is the to better understand the view of R0. In our model, R0 is 2.58792. So R0 is 2.58. So more than that. So this is the plot. Now this is the most important thing that we have drawn in our model, the effect of intervention strategies. So this curve, this red curve is showing there is no intervention strategy. So we perform beta P as we consider beta P decreased by 1 minus omega into beta P. When omega equal to 0.0, you can see that no intervention strategies is made, so R0 is 2.0490. So there is a high peak, and if we use lockdown phase 3, say omega equal to 0.2 we considered, so R0 is 1.6392. So curve will be decreased because this is the green line. This green line is showing that curve is decreased here. But if we increase R0 equal to 0.5, omega equal to 0.5, so R0 is 1.0245. So curve will be decreasing here. So again, if we consider omega equal to 0.8, the curve is decreased and R0 is become very less than 1. So this can be diode. So if we use the intervention strategies, means beta P replaced by the intervention strategy by using lockdown, say 1 minus omega, by using defined values of omega, you will see without lockdown the curve is showing this, and by using lockdown with by maintaining social distancing and other intervention strategies, the curve is being decreasing, and the curve is being decreased. And what happened in the time series analysis, you will see for without intervention strategy, the peak is here, increasing here, starting from here with high rate, with the highest peak. But if we use omega equal to 0.1, the peak is occurring delay. So you will see the peak is decreasing here. Here the peak is here, but if we increase the value of omega, the not only occurring the peak with high rate, but peak will be decrease here. Also, if we increase the omega, then the peak will be decreasing here, also occurring the causing is here. So in the figure you will see that I have seen in the previously that lockdown not only affect the size of the peak but also influence the occurrence of the peak. That means the effect of lockdown reduces the size of, not only reduces the size of peak but also causing delays in occurring on the peak. So when we engage in causing delay, also size of the peak. So our model also produces the same kind of figure for the case of lockdown that I have sent in the previously when we explained the model. So our model is little bit will give the most of the good dynamics actually. And also another thing, when we calculate the R0 less than 1, so there is no disease. R0 greater than 1, so the disease free unstable and disease will be outbreak. So this is the bar, R0 is the threshold. Where the left side the disease free and the right side become the disease, substantial outbreak of the diseases. So R0 also playing a role in the disease outbreak, when the disease will die out or the disease will be outbreak in the community. So R0 playing a role in the disease outbreak. In another figure we have from the long time dynamics, there is a long term dynamics. This is previously I have seen, and there is decreasing, and we have seen the long time dynamics, but here we have seen that there is a peak and occurrence of another peak also there. So there is a transient dynamics of the seasonal effect can be shown. So in the case of there is a peak, also there is very few lockdown, but in case of there is a lockdown, there is also peak of the COVID-19 cases. So we can conclude that the COVID-19, in order to mitigate the COVID-19, we must have to maintain the social distancing. And also in the study we have mentioned the basic reproduction number, and we may also conclude that the herd immunity is necessary for maintaining the for controlling the COVID-19 cases. And also in the model that we have studied earlier, that model also give an outbreak that we can say that the second wave may arise, and this is showing the case. And these are the references. You can see the good book, and these are two are very good books. In that book, you can see the basic reproduction number and other uh, ideas about the COVID, about the infectious diseases, and these are our all. Also, this some other story, and this is one of the good reference. You can see here the R0 and different kind of R0s, etc. And thank you all for uh, listening my lecture, and thank you the organizer for giving the opportunity actually, and thank you all. Hello, is there any question?
So, thank you
Hello.
so much, sir. Okay, participants, you are unmuted. So, if you have any question, then you can ask to the Professor Subhaji. So, is there any
Yes, yes,
question, participants?
yes. Any question please from the participants?
So, if there is no question, then let me thank Professor Subhas Khajanchi for his nice
Okay,
lecture.
thank you very much. But I don't know. Maybe the maybe I am unable to give the overview about the diseases to all the people. That's why no one has no question. So it is very bad thing that maybe no one understand my lecture or whatever I am
That is not
saying.
true,
No
sir.
one understand.
The second part, maybe the participant has understand everything. It is also, it can be also true. So, if there
True,
is no
but in the
question,
first part, I have tried to give the overview about the diseases, how can find the basic reproduction number and other things also. Yeah. Okay, please tell me, sir.
okay, so I'm very thankful to Professor Subhas Ajanchi for his nice deliberation. And I think the
Okay, thank.
participants have must enjoyed this lecture because this lecture is very relevant in the present scenario as we all
Yeah,
are
that's
suffering from this COVID-19
COVID.
and second wave of this pandemic. So
Yeah,
I hope this lecture maybe was very informative and quite impressive. So the participants must have enjoyed this lecture. So let us conclude this session here. Now the participants are requested to come again to please join again on tomorrow at 9:50. We will have a lecture of Professor Vinod Kumar Mishra on Maple. After that, we will have two sessions on LaTeX, which will be very useful for the participants in documentation, in typesetting a document, or for the better presentation of a document. So,
thank you very much, sir. Is there any question? Please ask me, sir. But this is the basic reproduction number. You are working on that only. So you and your student may have some question, but your student also not asking anything, sir. Okay. Thank you, sir. Okay.
okay. So thank you so much for joining this, for giving this
Okay.
deliberation, and participants are requested to come again on tomorrow at 9:55. So thank you so much for your talk, sir. So let us conclude this
Okay.
session here. Yeah, thank you so much.
Thank you.